Hello everyone. I'm Devasti Bormai from Department of Physics, University of Science and Technology, Meghalaya. Today, I'm going to discuss about the topic nuclear radiation and its application and its effect and various detection techniques. In the first part, I'll basically discuss. This is the first part of this discussion. So, in this topic, I'll basically going to discuss about the what is nuclear radiation and why it is important, how it's happened, and what is the causes of the nuclear radiation. That part I'm going to discuss in this presentation. So before going to the start of this actual topic, let's discuss why this study of this nuclear radiation is very much important for us. So basically, understanding nuclear radiation is essential for maintaining the safety of nuclear power plants, nuclear reactors, and other nuclear facilities. It enables the development of robust safety protocols, accident prevention measures, and effective emergency response plans. Knowledge of nuclear radiation is vital for establishing appropriate safety measures to protect workers, the public, the environment from the radiation exposure in medical, industrial, and research settings. Nuclear radiation plays a crucial role in medicine, enabling diagnostic imaging, cancer treatment, and nuclear medicine procedure. Research in this field improve the medical technologies and patient care. Monitoring and studying the nuclear radiation are crucial for assessing environmental impact resulting from nuclear accident, nuclear weapon tests, naturally occurring radioactivity. It aids in understanding and mitigating potential risks to ecosystem and public health. Properly handling nuclear waste from power plant and other nuclear activities requires a deep understanding of property and behavior of radioactive material, ensuring safe storage and disposal. Radiation in space poses a concern for space mission, and understanding cosmic radiation helps protect astronauts during space travel. Nuclear radiation research contributes to our understanding to atomic and nuclear physics, leading to advancement in fundamental science and technology. Studying nuclear radiation support effort to detect and monitoring nuclear materials, preventing the proliferation of nuclear weapons, enhancing national security. Research on nuclear radiation aid in development of innovative and sustainable nuclear energy technologies, contribution to global energy mix, and reducing greenhouse gas emission. Overall, the study of nuclear radiation is vital for ensuring safety, advancing medical treatment, protecting the environment, enhancing scientific knowledge, and addressing numerous challenges related to nuclear science and technology. So, let's see what are the topics which I am going to cover during this presentation. Uh, so these are the topics which I am going to discuss. So first of all, try to give a brief introduction about the nuclear radiation and radionuclide. Then different sources of radioactivity I'll discuss. I'll also discuss the uranium 238 decay, effect of radiation detection technique, and then I'll give you the conclusion part. So let's start from the introduction part. So in the introduction, let me introduce you what is nuclear radiation. So nuclear radiation basically refers to the release of high energy particles or electromagnetic waves from a nucleus of unstable atom. This emission can be in the form of alpha particles, beta particles, or gamma rays. Radionuclides are radioactive isotope of elements with unstable nuclei. They emit nuclear radiation as they undergo radioactive decay to reach a more stable state. This process can result in the transformation of one element into another, and it releases energy in the form of radiation. So the radioisotopes radioactive nuclei are also called as radioisotope, radioactive isotope, radioactive nuclei. So, how these radioactive particles or radioisotopes are discovered? So, he is the man who is known as Henry Becquerel, discovered this radionuclide first, and later on, Madame Curie and her husband Pierre Curie um, continues the work, and they discovered this radionuclide. So, how this in 1896, Henry Becquerel accidentally discovered this radioactivity while he is studying the property of fluorescent mineral. He observed that certain uranium cells emit penetrating rays that could expose photographic light even when sealed from light. This led him to the realization of uranium was emitting a new form of radiation which he named as uranium rays. Shortly after Becquerel's discovery, Marie Curie and her husband Pierre Curie become interested in the phenomenon. They conduct extensive research on radioactive mineral, focusing on pitchblende, a mineral containing uranium. In 1898, they isolated two new elements from pitchblende, which turned out to be highly radioactive polonium. This name is given by Mary's home country, Poland, and Radia. The discovery of these two radioactive elements revolutionized the understanding of atomic structure and radiation, and it earned Marie Curie the Nobel Prize in Physics in 1903, making her the first woman in receiving the prestigious award. Radioactivity is caused by instability of atomic nuclei. There are several regions of instability. First of all, when the atoms with an imbalance in number of neutron and proton in their nucleus are often unstable. This can lead the emission of particles by acid a more stable configuration. When an atom captures an additional neutron, it can become unstable and undergoes radioactive decay to reach a more balanced state. Some heavy metal can split two or more smaller nuclei, releasing energy and additional neutrons, which may go to the cause of further fission reaction in a chain reaction. Then high energy particles such as those in cosmic ray or form a nuclear reaction can excite the atomic nuclei and leading to the instability and subsequent release of radiation. So there are several processes of emission of radionuclide. So first of all, let's discuss about the alpha decay. So uh, the process resulted in the emission of alpha particles. So alpha decay is a type of radioactive decay in which the atomic nucleus emits an alpha particle which consists of two protons, two neutrons, essentially a helium nucleus. During alpha decay, the original nucleus loses two protons and two neutrons, reducing its atomic number by 2 and its mass number by 4. During alpha decay, the unstable nucleus loses two protons and 2 neutrons, reducing its atomic number by 2 and mass number by 4. As a result, original element transmuted into a new element with an atomic number 2 unit lower and mass number 4 unit lower. The emission of an alpha particle releases energy and newly formed nucleus may still be unstable, leading to further decay process until it reaches a stable configuration. The alpha decay process is characterized by well-defined alpha decay constant, which determine the rate at which the decay occurs. The constant is unique for each radioactive isotope, allowing scientists to predict the decay rate and studying the property of radioactive materials. Next one is your beta decay. So beta decay is a type of radioactive decay in which an unstable atomic nucleus undergoes a transformation by emitting a beta particle. There are two types of beta decay, negative beta decay and positive beta decay. In negative beta decay, a neutron in a nucleus is transformed into a proton, an electron, and a neutrino, and an antineutrino. The newly formed proton remains in the nucleus while the electron is emitted with high energy. The atomic number of nucleus is increased by 1, but the mass number remains the same. In positive beta decay, a proton in the nucleus is transformed into a neutron, a positon, and a neutrino. And the newly formed neutron remain in the nucleus while the positron is emitted. The atomic number of the nucleus decreased by 1, but the mass number remains unchanged. Beta decay occurs in the nuclei that have either too many protons or too many neutrons, causing an imbalance. By undergoing beta decay, the unstable nucleus moves towards a more stable configuration and the emitted beta particles carries away excess energy. Beta decay plays a crucial role in the decay chain of many radioactive isotopes, contributing the natural radioactivity of elements. It also has practical application in various fields, including nuclear medicine, where positron emission tomography relays the detecting the emitted positron to create medical images. Next one is gamma decay. Gamma decay, also known as gamma radiation, is a type of radioactive decay that involves the emission of gamma rays from an atomic nucleus. Unlike alpha and beta decay, gamma decay does not involve the emission of particles with mass. Instead, it releases high energy electromagnetic waves called gamma rays. Gamma rays are a form of electromagnetic radiation similar to X-ray but more energetic. They have no source and no mass, and they travel at the speed of light. Gamma rays have very high penetrating power and can pass through most materials requiring dense materials like lead or concrete for effective shielding. Gamma decay typically follows alpha or beta decay when a nucleus is in an excited energy state. The emission of gamma rays allows the nucleus to release excess energy and transition to a more stable state. The process does not alter the atomic number or mass number of the nucleus. It only changes the nuclear energy scale. Gamma rays are widely used in medical imaging, industrial applications, scientific research. In nuclear medicine, gamma cameras and PET scanner detect gamma rays emitted by radioactive pressure to create diagnostic images. In industrial application, gamma rays are used for non-destructive testing of materials. In astrophysics, gamma rays provide valuable information about high energy phenomenon in the universe. Next, let's discuss about the penetrating power of alpha, beta, and gamma rays. The penetration power of alpha, beta, and gamma radiation refer to their ability to pass through different materials. It is an essential factor to determining the potential hazard associated with exposure to each type of radiation. So in case of an alpha particle, alpha particle has the lower penetration power. They can be stopped by a sheet of paper or the outer layer of human skin. However, alpha emitting radioactive material can possess significant health risks if inhaled or ingested. They can be cause damage to nearby tissues of the cellular level. So next, beta particles. What are the penetration power of the beta particles? So beta particles have the higher penetration power. compared to the alpha particles. They can pass through materials such as paper and clothing, but can be stopped by materials like plastic, glass, or aluminum. Beta radiation can penetrate the skin and cause damage to the living tissue. So, it is a concern if the radioactive material is on or near to the body. Next one is the gamma rays. Gamma rays are very high penetration power. They can pass through a wide range of material, including paper, clothing, or most metal. Gamma rays require dense materials like lead, concrete, or thick steel to effectively shield against them. They can penetrate the body and cause damage to tissue at greater depth, making them a significant hazard for external and internal exposure. The varying penetrating power of these radiation types influences the safety measures required for handling and protecting against them. Shielding and distance are crucial considerations in minimizing exposure to alpha, beta, and gamma radiation. So now coming to the next point, which is the sources of different sources of radionuclease. Basically, it is categorized into two parts. First one is your lesser radioactivity or lesser radionuclease, which is produced from the necessary radioactivity. Next one is your artificial radionuclide. So, depending on the characteristic of the natural radionucleus, it is again categorized into two parts. First one is the primordial radionuclide, another one the cosmogenic radionuclide. So, let's discuss about the natural radionucleus. So, radionucleus contributes, natural radionucleus actually contributes to background radiation, which is the radiation we are exposed to from natural sources every day. While they are generally present in the low concentration and do not pose significant health risks, certain geological formation or environmental condition can lead to higher level of exposure. Proper monitoring and understanding of natural radionuclides are essential for managing potential health risks associated with the radioactivity of the environment. So coming to the primordial radionuclide, primordial radionuclides are subset of natural radionuclides that have been present since the formation of the earth, and they have long life, very long life. These radioactive isotopes are remnant in the primordial radionucleosynthesis that occurred during the early stage of the universe and are part of the Earth's natural radioactivity. The term primordial refers to the fact that these radionuclides have survived throughout geological timescale with half-lives ranging from millions to billions of years. They are typically found in the earth crust, mantle, and certain rocks and minerals. Some examples of primordial radionuclides are uranium-238, thorium-232, potassium 40, lead-210, radium-226, etc. Due to their long half-lives, primordial radionuclides contributes significantly to breakdown radiation on Earth, which is the radiation that humans are exposed to from natural sources. While they are generally present in low concentration, they can become more concentrated in certain geological formations, leading to increased radiation exposure in specific areas. Primordial radionuclides play a crucial role in geochronology and the study of Earth history. They also have implication in understanding the evolution of the Earth mantle, the age of the rock and minerals, and the formation of the solar system. Additionally, they can influence the necessary radiation exposure experienced by human population living in region with higher concentration of these isotopes. Coming to the cosmogenic radionuclides, they are radioactive isotopes that are produced in the Earth atmosphere and surface material by interaction of cosmic rays with atomic nuclei. Cosmic rays are high energy particles, mainly proton and atomic nuclei, originated from the outer space. When cosmic rays collide with the atoms in the atmosphere and surface rock, they can induce nuclear reaction, leading to the production of a new isotope. Some of these isotopes are radionuclide with relatively short half-lives, while others are stable isotopes. So, cosmogenic radionuclides have various applications in different fields. By measuring the abundance of certain cosmogenic radionuclide in rock or sediment, scientists can determine the exposure age of geological surfaces. It helps in understanding the timing of landscape change, glacial glacial retreat, and erosion rate. Cosmogenic radionuclide dating technique can be used to date archaeological artifacts and human-made structures that have been exposed to cosmic radiation over time. Cosmogenic radionuclides can provide valuable information about past climate variation and erosion rates, helping to reconstruct environmental changes. The measurement of cosmogenic radionuclides in meteorite and lunar rocks helps scientists learn about solar activity and history of the solar system. Some example of cosmogenic radionuclides include beryllium 10, carbon 14, and aluminium 26, among others. These radionuclides serve a powerful tool in various scientific disciplines to gain insight into Earth's story, past climate variation, and processes shaping the Earth's surface over long periods. Now coming to the artificial radionuclide, it's also known as synthetic or man-made radionuclides, are radioactive isotopes that do not exist naturally on Earth. They are produced through various nuclear reactions in laboratories, nuclear reactors, particle accelerators, and other artificial processes. Scientists can create artificial radionuclides by bombarding stable isotope with neutrons, protons, and other particles. This nuclear reaction changes the number of protons and neutrons in the nucleus, resulting in the formation of new isotopes with different properties, including radioactivity. Artificial radionuclides have a wide range of applications in medicine, industry, and research. In medicine, they are used for diagnostic imaging, cancer treatment, and therapeutic procedures. In industry, they are employed for radiography, gauging, and sterilizing. In research, they serve as tracer and marker to study biological processes and environmental behavior. While artificial radionuclides have numerous beneficial applications, they require carefully handling and disposal due to their radioactive nature. Safety measures and regulations are in place to ensure their proper use and minimize potential risks to human health and the environment. So here I conclude for today's talk. In the next class, next presentation, we'll discuss about the uranium decay. Then we'll discuss about the various effects of radionuclide And also we are trying to discuss about the various detection techniques such as scintillation detectors, one passive detectors known as SSNTD, solid state nuclear track detector, and we also try to discuss about different techniques of which helps to detect the different types of radionucleus. Thank you so much. Thank you for your kind present. Thank you.